I have here is a laptop. So I don't have two different screens, which means that I can't have like one set of things open here and then proper space here. So I don't know how that's going to affect things. I've got my set of notes, present, but it's like I can only look at them and work here. And I'm also on maybe a slightly less stable writing surface than I'm used to. So hopefully I don't knock the pin pad off um, in the middle of notes. So those are the caveats. Welcome back, I guess, after the long weekend as well. It's been almost a whole week since our last class as a result. And I'm happy to say I do not have jury duty, so I don't anticipate any weird time classes. They canceled it and said you don't have to, you know, report in or do anything further.
Awesome.
Whether it's because of the weather or whether it's because they just settled whatever case it was or what, don't know. But I'm not going to look that gift horse in the mouth by asking. um, where we had left off in our notes, I had done we kind of had started in on momentum eigenstates and talked about the momentum eigenvalue and the de Broglie relations. And then I kind of stopped there because we weren't going to have time to do um, really the next thing, which was degeneracy. And awkwardly, maybe, or unfortunately, this is not the best place to have stopped. I wish that we had had like maybe another 30 minutes or 20 minutes because it turns out that therefore today we'll do a little bit of degeneracy, a few more notes about momentum eigenstates, and then depending upon how long we decide to do class for, Dirac normalization is like the next topic, and it's in some sense long enough that I don't know that we'll finish it, but also short enough that it's not a whole nother day's topic. So let's start with degeneracy, and then we'll go from there. Um, we had stated already that um, we're looking in kind of momentum space. Let me shift this over to my little workspace. Dang, I hear the stupid dog barking in the background. Are you guys hearing that?
No,
Okay.
the team's noise canceling is really effective.
It is. It is, and I'm glad because this morning I basically taught all my courses this way today because I wasn't sure what the road conditions were going to be. Now, ironically, I'm about to head in to do my afternoon labs, but it's like it should be warm-ish enough that they've dealt with it by now. But all morning it was you could hear in the background my wife singing, my kids fighting, the dog that we brought inside barking. But the noise cancellation maybe fixed all that, so it just looked like I was a very distracted person for no reason. Um, so with that stated, recall that we're kind of looking at momentum eigenstates, and that one way that we can sort of write these eigenstates for ourselves is by doing something along the lines of, okay, I don't know what that was all about. Oh, this is not the tool that I want. Do this. Sorry for the little setup time. Okay, momentum eigenstate. That's really sketchy. Can you guys read that okay?
So far, so good.
Maybe I will not use this particular tool for this particular thing. I usually have actually 3 pins up here that I can use. And it's just throwing me a little bit off because of this. So we're still in X representation, but we're looking at the momentum eigenstates within this representation. And note that both of these states, which we can represent this way, will give us the same energy values. Switching pins. Because at the moment, V is 0. Doesn't really matter if it's 0 or non-zero, by the way, but at the moment it's 0. So my energy is given by whatever my momentum is squared over 2m. And so both of these states should give me the same value for energy when I square the momentum value, essentially. Okay. And so since we have the same result for both, same energy for 2 states, this is what's called degeneracy. So this is twofold, as it turns out, degeneracy. Okay. And with respect specifically to momentum, and if you were to go to more dimensions, remember that we're basically looking right now at one-dimensional unbound state. Now imagine a two-dimensional unbound state. So what does that essentially mean? So 2 dimensions, 2D. This momentum, this momentum, this momentum, and this momentum all give me the same results. And that's strictly forcing the thing to either have an X or a Y momentum. If it can have some other momentum, some skew momentum. So you can imagine that we have quite a bit of possible degeneracy here. Okay. So with that in mind, let's talk classical degeneracy as a very simple example. Suppose that you took 2 dice, 2 plain 6-sided dice, not 2 of the dice that I use to call on people in my larger classes where there's 8 sides and 12 sides and that kind of thing. We're not doing like a D&D dice set here. Just 2 plain 6-sided dice. Okay, maybe you're going to roll the 2 dice, and the numbers that you get on the 2 are sort of like your measurements, right? So then instead of saying your measurement is the individual numbers, your measurement is the sum of these 2 dice rolls. Okay, so I have, for example, roll 1 die here, and maybe I get this. Okay, and then the other die I've rolled, and it comes up like this. So this would be converted to the measurement 5.
Yeah.
Basically just add them together. Okay. So now we ask, what kind of degeneracy do we have from the dice? And the answer is, well, depends upon what the measurement is. So measuring, we'll put our measurements here. And then our degeneracy here. And then, for example, combinations. Okay, so we could measure 2. There is no degeneracy here. There's only one way to get a measurement of 2. You have to have snake eyes. You have to roll both die as a 1. So 1, 1. All right, now measure 3. What kind of degeneracy do we have for that? Well, it's twofold because I could roll 1, 2, or I could roll 2, 1. And if that's confusing as to how I'm doing that, imagine, if you will, that instead of having 2 identical dice, I'm tracking which die is which. And so this would be like the blue dice being a 1. This one would be like the blue die being a 2. Okay. Now, I'm not going to do this for every one of them because that's going to be cumbersome, but this gives you the idea of what I mean by 1, 2 versus 2, 1.
Mm-hmm.
Okay. So now, how do I roll a 4? Well, this one is actually threefold degenerate because I could go 1, 3, 2, 2, or 3, 1. If I want to roll a 5, like what I've got up here, this one's actually going to be fourfold degenerate. Okay, so I could go 1, 4, 2, 3, 3, 2, or 4, 1. And we can continue that with the other dice. Rolling a 6 is fivefold degenerate. Rolling a 7 is sixfold degenerate. Rolling an 8 becomes fivefold degenerate. Rolling a 9 is fourfold. Rolling a 10 is threefold. Rolling an 11 is twofold. And when you get to a 12, once again, there's only one way to get that, and it's 6s on both die. Okay. And this is a very simple version of this degeneracy problem because there's only 2 dice involved. Imagine rolling like in Yahtzee where you have, was it 6 die or 5 die? Or in Farkle where you have, I think it's 6 again. Different games where you have multiple dice that you can roll. Even though the dice themselves are identical, there's different combinations that give you different, the same number, if you will. Okay, so this is your classical degeneracy. And with dice, there are 11 for 2 dice. There's 11 possible measurements, 9 of which have degeneracy. And the level of degeneracy in this classical dice rolling case kind of correlates with what's the probability of measuring that number, of rolling that number. So the most probabilistic roll for a pair of dice is a 7. 6 ways of doing it, you have a 1 in 6 chance of rolling a 7. Okay. And so if you're playing, there's certain games you can play like Settlers of Catan, where you roll 2 dice and you figure out how much of each resource do you get. And it's based on what number you've measured here, what's your dice roll. And so the strategically best numbers to pick, to sort of like harvest resources on, would be 6s and 8s. 7, as it turns out, is you can't pick. So of the pickable numbers, 6 and 8 are the best, and then 9 and 5 are the next best, and so on, statistically. Okay, so that's degeneracy, and this will come up throughout this semester. We will find systems that are degenerate in one way or another. Okay, so coming back to momentum eigenstates. So what does our wave function look like? What does this function right here, phi p of x, how might we represent it? Well, usually we have to give it some sort of an amplitude. And then we have essentially some sort of phase term, which is I times P times X times H bar. Okay. And this right here could be broken into a real and an imaginary part. So in other words, this could be written as A times cosine pxh bar plus A times I times sine pxh bar. So, sorry, I left off a divided by in here. So this right here is your real part. This right here is your imaginary part. And if you were going to plot the two of them, well, you guys know what sines and cosines look like. So for the real part, I basically expect something like this. That's not very good. And for the imaginary part, plot it on the same one, but in red. I expect something more like this. Okay, where what I'm plotting is essentially real or imaginary part of phi p of x versus x. Okay, and so I can label for myself things in here such as the wavelength. Label it in kind of this color. So from peak to peak, this would be my wavelength of my real part. It's also should be equal to the wavelength of my imaginary part. Okay, and I can say that this wavelength should be 2 pi divided by wave number k, which from our discussion last time of the de Broglie wavelength should correspond to 2 pi times h bar over p. Okay, or if you prefer, just h over p, and that's true for both the real and the imaginary part. All right. Now, we do need both in order to really describe this wave. And if you want to get the time dependence of this wave, this right here should look like your wave times e to the negative I times your energy that corresponds to this eigenstate, T over H bar. And noting that the energy EP is actually P squared over 2M. What this ends up giving us is psi of x comma t is this original eigenstate e to the negative I p squared t over 2m h bar. Or if you want to put it in terms of this state right here, as written here. So we're doing that substitution. And I don't really want to have them both circled because, again, I'm uploading these for you guys. This right here will end up like this. I will have A, E, and then let's just combine all the exponential and phase terms as best we can. We'd have E to the I, and then P over H bar times X minus PT over 2M. Now that PT over 2M term, that looks a lot like, or maybe I should say, given that we have P over H bar, that looks like a K. And then the P over M part looks like a V. So this looks suspiciously like you have a traveling wave, except for that we have this one caveat. Whoops. Keep it in this color. If V is P over not M, but 2M, then you have your traveling wave. That's getting a little cluttered. And basically we're saying recall that P over H bar is your wave number K. Sorry, I didn't give you very much time to write that down. Okay. So you have a sine wave, you have a cosine wave present here, right? For the real part, for the imaginary part. And essentially, what the claim here is, since we've had to make V be P over 2M rather than V equals P over M, essentially that means that these waves are traveling at half of the speed or velocity that you would have found classically in a classical particle. Okay, so classically, P is mv. Here, we need to have V is P over 2M. Okay, so there is an apparent, and I note the word apparent, discrepancy between quantum wave velocity and classical particle or wave velocity. But where that apparent difference is that we have kind of two velocities kind of hiding in sight here. You have on the one hand what's called phase velocity, and on the other hand what's called group velocity. So what are these two things? So phase velocity in this case, phase velocity always is omega over k. Group velocity is d omega over dk evaluated at whatever the sort of central wave number to your group is. Okay. I'm putting this here. I'm going to actually leave it alone for now. There's something else that we have to do before then, which is what about normalization? These states are not very well normalized at the moment. So this is an idea that we're going to come back to. But in um, a very simple term, a simple way of thinking of this is your wave might be traveling as a wave packet. That wave packet contains more than one sort of wavelet or wave frequency component, if you will, within it. This right here is in some sense giving us what's the speed at which those frequency components are moving within your wave. This is giving us the speed at which the whole wave packet together moves. Now, which one is the actual, let's say, measurable data? Which one do we actually typically measure or associate with the wave itself's motion? The answer is this one. This is the speed at which information can be carried by that wave. All right.
Can I ask a question?
Yeah, sure.
So in this, I know the de Broglie wavelength, but normally within this context, I'm thinking about photons, where it really applies between wave and group velocity. So the wavelength of the photon, this is an interesting discussion because it really explains how a photon can pass through a material with some indice and maintain its wavelength, right? So it slows down the group velocity, but the wavelength is defined within that phase velocity then. Is that right?
Well, when a photon actually interacts with a medium of different um, uh, uh, refractive index, yeah, the group has to slow down. The individual phase velocities, they may interact with it as well because it turns out that k for those can also tie into that refractive index. Put differently, you can always in practice maybe you can't. How do you make a photon of one wavelength? What does it need? What is the property of it? Well, essentially, what you have is a continuous wave that has infinite duration and that has interacted with nothing.
Yeah,
That's it.
I don't want to get into the whole, I don't mean to derail the discussion with trying to push you into the infinite bandwidth and finite wavelength,
Right,
space.
right.
But yeah, so to me, it's like though if the wavelength and the speed are interdependent, and light slows down in a material of index refraction, you should have some sort of a color shift, but you don't see that, and that
Right.
must be because the color is defined, or the wavelength is defined within that phase velocity that doesn't change.
Yeah. Or a different way of thinking of it is maybe it's better to think of it as the color is tied to the frequency more
Right.
so than to the wavelength. Because if hypothetically you had a
Okay.
single wavelength continuous wave beam of light that interacts with your um, refractive index, you have two options. You know that it's going to slow down. So either your frequency has to change or your wavelength has to change or both, but at least one of the two must change, even for that single
Hmm.
frequency, not a wave packet light. Well, the frequency, as it turns out, is what's tied to energy within that wave. And so energy conservation basically requires that not change. Now, the wavelength changes, therefore, as a result, because your speed has changed and your frequency has not. But now, thinking back on this, energy is tied to frequency. How do we actually see? Because color is really more of a physiological response to light.
Right.
how do we actually see different colors? Well, essentially, there's some interaction with between the light that we're seeing and the rods and cones in our eyes, and that energy, that interaction is energy based. It has to do with promoting essentially like electrons in the band of the, I guess it'd be the cones for color vision, promoting those from a lower state to a higher state. But that's inherently an energy dependent process. And so color must be tied to energy, which is tied to frequency, which is the unchanging thing within your medium.
Okay.
There is maybe a second thing to be said there, though, even with all else being kind of equal. Your that photon eventually, in order for you to see it, in order for you to see the color at all, the photon enters your eye. And once it's in your eye has a particular set of properties for including refractive index. And so by the time it actually gets to your rods and cones, it's already set at whatever that particular wavelength, that particular frequency in the eye would be. Now, is there a way to test that? Yes, but I think it would cause a bit of harm to somebody to do
Right.
this. Essentially, if you could get their eye to actually change somehow in refractive index by heating it, cooling it, injecting something into it. But you can see that this is really getting into the weeds now, because now we're
Yeah.
talking experiments with humans, test subjects, and
Yeah, well, so the genesis of the question for me is like this fundamental question kicking around of if light has momentum, where does and energy is conserved, then where does it go when it slows down in a material of index of refraction, and where does it come from when it accelerates on the backside, right? And I think you answered that question by saying the energy really is in the frequency and it's constant throughout.
right, right. Although it does kick the can down the road a little bit because momentum is tied to wavelength. And so now you have to figure out what's going on there.
Right.
And, one way, and again, we're going back to a classical discussion by doing this, but one way of thinking of it is when light interacts with stuff, there actually is a force between light and the thing that it's interacting with. It's even measurable for sufficiently much light or a sufficiently large object. It's usually actually a pressure that you get. And so you get enough light, now you've got a force that you can measure um, via that pressure. And so if you have light that hits a transparent medium, so maybe I happen to have some medium like this that's transparent and light is going to pass through it. Let's say that the light comes in red. Any light that's being absorbed is actually depositing some amount of pressure on this thing, such that this thing actually ends up having a recoil in this direction. That's one way, not the only way, but it's one way that solar sails could be made to work.
Hmm.
Now, those are also using the solar wind, which includes particles beyond light. But in principle, there are ideas for could we make a solar sail that we push using just a laser? And that's how this would work. And that's usually just okay, so we're absorbing the light or maybe reflecting it off. But now suppose that the light passes through this medium, comes out the other end. What's happening there? Well, that essentially means that if you have the same amount passing through as you had go in, so if this is I naught and this right here is also I naught, then if you had anything being absorbed on this end, it has to be getting re-emitted, and it has to be getting re-emitted on this end in this direction.
Mm.
And so momentum does end up actually being conserved for this system classically. Now, what usually actually happens is you don't get I naught here. You get some fraction of I naught. So let's say 95% makes it through. So that difference between this and this is how much has been absorbed. That's your expected change in um, essentially in momentum, if you will, is due to the pressure from absorbing that much light. And so this thing, if it was just allowed to move freely, would in fact start moving.
Wow.
Now, how do you set that up terrestrially? Um, this is usually a really small effect for one. You'd want a very nearly frictionless surface, and you'd want a big and high energy laser to get the most bang for your buck. Can it be done? Well, I don't have anything that's strong enough to do that. But I imagine you could buy, if you have a couple $100,000, $250,000 lying around, you could buy um, like one of those 1 to 2 joule 9-ish nanosecond indie YAG lasers that Newport and Thor Labs and Thales and so on, all the big producers have them. And then you could set that up and aim it at something that is just absorbing and put on a frictionless level air track. You probably could actually measure some recoil, even in those conditions.
I was thinking about as you were describing that, I was thinking about maybe like a reflective paddle wheel in a vacuum.
Yeah, yeah, you could do that. You have friction to overcome with the between the wheel and the axle, but yeah.
Mm-hmm.
Um, so Dirac normalization is about 2 pages worth of my notes. I'm not entirely convinced that we'll get through that in a reasonable time unless you guys want to stay a little over.
I'm good.
You good for today?
I'm good for
Or are
staying
you
a
good to
little
stay
over.
over? You good to stay
Yeah.
over? Chip, James?
How long are we talking? Because I do have something at like 12:15.
Um, maybe. Maybe.
I mean, I can probably stay on here till like 12:05.
Okay. Let's see if we can knock it out in that time. James?
Yeah, that's fine.
Okay. So Dirac normalization. Um, complex square of the wave should give us a probability density. In other words, I forget how I was writing probability density last semester. I changed my notation a little bit each time, but we'll use this as probability density. This should look like this right here squared. Okay, and that in turn is psi of x, or phi of x, excuse me, star times phi of x. Okay, and then probability itself of measuring between 2 points, as you know, let's say x1 less than x less than x2, should look like the integral from first point to second point of this probability density. Okay, and so obviously going from minus infinity to infinity, this probability should come out to 1. Okay. So what is this product going to give us? Well, going back up to, I have to go up a couple slides here. I have to scroll up. Going back up to what we have here, or really, I'm looking at things being a little silly. Looking at what I have here. Okay. If I want to take the complex square of that, sorry, it's what I have here. If I want to take the complex square of that, what am I going to end up with?
What are we squaring?
Well, basically we have e to the I like so, and we're squaring it. Well, this term right here, by definition, is just some phase because of this imaginary component. And so what we're left with is just amplitude squared. Okay. And so this basically means that our probability density for a momentum eigenstate is just some constant which is position independent. In other words, if I wanted to plot it, here's position. Here is this term here, phi p of x squared. And if I'm plotting it, all I get one of the most boring plots in the world, a horizontal line. Okay. Now, this should be obviously problematic, right? Because I just said if this thing right here is integrated from minus infinity to infinity, just put it in these terms here. I have to get a value of 1. That's my probability of finding it from minus infinity to infinity. But this right here is just the same thing as finding the area bounded by this curve. So the area bounded by this whole curve has to be 1. But I just said that it might stretch from minus infinity to plus infinity, and I've come up with some amplitude here. Okay. So mathematically, this is a problem because it's not actually normalized. Conceptually, it's a problem because we kind of expect our particle to at least be somewhat localized. It may not be exactly localized right here. We expect it to be like high probability of being maybe in this region, for example. And this right here seems to contradict both of those things. So basically, we can solve both of these problems by basically making a superposition of momentum eigenstates. Okay, and these will then give us a wave packet, which is what we were talking about kind of earlier in a roundabout way. So we've now come full circle in some sense. Okay, and so as far as like wave packets per se, that's actually part 2 of this lecture set. So that's definitely a future day. But let's consider the important properties of our base states again. Okay, so we have orthogonality, word which I cannot spell to save my life. Whoops, a little ahead of myself there. So state AI, state AJ that's not equal to I must be 0. Okay, normalization, that's state I is 1. Or if you want orthonormality, then state I, state J is your delta function, dij. And then the third one is completeness. Okay, and completeness means take the sum on I of this outer product. And what you should get is the one vector, the identity vector matrix, excuse me. Okay. And this, of course, is your Kronecker delta. So that is not how that is spelled. It's K-E-R, might be H-E-R, remember. Okay. All right, so those were discrete states. Now, what about these momentum eigenstates? What are we going to have for those? Instead of the Kronecker delta, we will use the Dirac delta. Okay, and so basically what that means is if I have some momentum states like this, these should equal to essentially the Dirac delta of the difference between these two momenta. Okay, and so what those will equal is infinity if these two are the same states, 0 if these two are not the same states. So this is called Dirac delta. I don't know if the D in delta is properly capitalized. All right. Now, this statement up here in integral form works out like this. All right, so this is basically orthonormality. So this whole thing, this is orthonormality for these states. Okay. Now, using our previously defined momentum eigenstates. Gosh, I hope I don't run myself out of slides here. Using the previously defined momentum eigenstates, what we have is that these states are A, E to the I, Px over H bar. Okay. It follows that, and there's a proof of this, but it's actually one of your homework problems if you are looking through the homeworks that I've assigned. So I'm not going to work it here. It's problem 6.7 in your textbook. Should be 6.7. 6.7 in mine. The 6.7 in yours say?
I'm looking. It'll probably take me a second to find it.
Okay. I haven't finished it though, but basically this is satisfied. Essentially is one over root 2 pi h bar. And that will satisfy the Dirac orthonormality condition. And then you can, in the problem, you then use that to normalize a specific state in wave vector state. Okay, but in any case, what this means is our normalization, our orthonormalization, orthonormality, whatever you want to call it, gives us this. So these now are our momentum eigenstates. And now they're sort of like properly solved. Okay. That, I think, is a good place to stop for the day, which will allow Chip to get where he needs to go and doesn't hold you guys too far over and all that. And it's a logical stopping point because we have a sort of conclusion. All right. So I will call it quits there. Do you guys have any further questions? Stop sharing and stop recording.
What page do you show problem 6.7 on in your book?